Okay, part two of processing a LiDAR derived network and making sure its flow paths are accurate so that we can get the most accurate output through our custom models. So I'm gonna I'm just gonna clean up my project a little bit so we know what we're looking at. Um, I've already saved this, so I'm just gonna bring in that saved layer. This is my, so you can see my culverts there on this DM. This is my new input DM to run, in this case through TauDem. Um, so what I do is I use command line. There's on TauDem's website, there is a guide to using TauDem command line functions, and I just I just keep this open. Um, there's installation instructions. Just skip that for now. Basically, what we're going to do is start this process. So the first step is to remove pits. So what I'm going to do is open the command line. I need to change my drive and change my directory. So I'm going to do that real quick. So I'm just going to navigate to that directory, copy the address, and paste that in. So now I'm in the working folder where these outputs, where it's going to look for the inputs and outputs. And in that folder I've specified, I have that DEM. Um, so now I'm just going to go to the command line and fastest thing, just copy the command and change the input name. So my input was named DEM, and now I just hit enter, and that is going to fill the pits in my DEM so that the flow directions and flow accumulations can be accurately produced. Once that is finished, it will put uh, a new file in my folder. So if I go in there, now I have a filled DEM. Um, and this is the step that I like to come in and look at the hillshade on this thing to see if we have any like major missed spots because it's really easy to identify on a hillshade. Um, so if you have your original LiDAR with a hillshade turned on and the hillshade of your filled DEM, and those are the only two things you have on, if you toggle between these two, you'll see places where you the pits are essentially filling. So um, one of the best examples is right here, this huge culvert, right? If you had burned in only 10 meters, you see how this pit essentially filled up to the point until it could spill through that culvert. If this was 10 meters, if this culvert was only 10 meters deep, it's going to fill way, way higher until it can spill through. And so this flat area would back up way upstream, and then you lose all the topography in this and lose the accuracy of where your stream network is going to be placed. And so it's easy to identify areas you may have missed by just toggling on and off a hillshade because you'll see that ponding effect in places where the culvert, in places where you missed a culvert where it's important to have one. So I'm looking at this, and there's really not many places that are glaringly standing out. Maybe some minor stuff on some small tributaries that I'm not too concerned about. But on on my main stem, I'm not seeing any like abnormal sort of reservoir ponding effect. And so I like this input. So I'm going to continue and go ahead with the next few steps. And I'm actually going to rename this just for the ease of the command line. Just call it FEL. So now I can go back to my TOWDEM guide. The next step is doing flow directions. So like I said, you could use tools in Q. You can use other tools, but this example is using TOWDEM. So I'm just going to copy that, do my flow directions, and make sure I change the input name. And I'm just going to get rid of these prefixes for my outputs and hit OK and let that run. Okay, that one's done. Run this other one real quick. The D infinity flow direction. And I forget if you need this. I just run it just in case. But you'll see what rasters you need in the future steps. So I'm just going to run all the both D8 and D infinity. But I think it actually just uses D8. Just something to be aware of. Okay, that finished. Next step. So we're looking at doing the contributing area. Like I said, it has D8 and D infinity. Pretty sure we're going to use D8. We use D8 and an outlet point to delineate the flow accumulation. And then we're going to go through some steps to delineate the stream network and threshold it. So I'm just going to run these real quick. I'm going to run both of them. Like I said, you probably don't need both, but just don't want to have to go back. And right here, at least in TOWDEM, it's important to put this -NC tag to make sure it's not getting contaminated by edge pixels. And I'm going to run that. Shouldn't take too long. And now I'm going to run the other one. Same thing. Okay, so this next step, when you look at it, you'll see it's asking for an outlet shape file. So the way TOWDEM works, it asks for this as an input to tell it where the stream is draining to. So I'm going to load this last output, this SCA raster, and you'll see roughly that drainage network we have. And right here's a good place to check to see if it's doing what you want. And it's easier to symbolize if you put it as like multicolor and turn down the max value. I like to change the opacity on the max value so that, or the minimum value to 0 so that you can see that hill shade on underneath. And now you can go zoom around and look at those places you had culverts and see if those flow paths are actually where you want them to. So I know we had a big berm up here that we wanted to make sure we got through. Or sorry, I apologize. This is not that raster yet to check. This one I need to go back to. I just need the outlet point. So I'm going to choose a point on the network layer. we're gonna go create layer, new shapefile, go to where we're saving our stuff, and just call it outlet. And it's a point, and we're in 11 North. Then you can just edit, add a point, hit OK, hit save, call it good, go back to our command line, and now we're going to create that flow accumulation. I'm going to do that same call out, and this is going to be our output, the 8080. This is an input, that outlet shapefile we just made, and the input here as well. Run that. That is done. We can pull that in now. It's not going to look much different, but you'll see what that outlet does is it removes, kind of clips down your raster and removes stuff that does not flow to that outlet point. So it got rid of that. If you had multiple outlet points, it would still include those, but we're not too concerned about those in this example. Now looking back at the command line guide, I'm going to skip this step. I don't need it as an input. We're going to use the Pucher-Douglas method of stream delineation. There's also a slope drainage area one, but this is a weighted grid to basically use as an input to the stream delineation. So this is the next step. So we're just going to copy and run that one. We don't need to change anything other than the names. Let that run. Okay, that is done. And now I'm going to run, we're almost to delineating a stream. I'm going to run this. I need to use that call out here again because we're doing a flow accumulation. So now we're using that weighted grid we just used to essentially rerun that flow accumulation. So it's kind of a copycat step, and hit run. Okay, finished there. So we're gonna load that output raster now, because the next step is to choose a threshold. You can try running this drop analysis. I like to just manually. You have to mess around to see what values make sense. I like to just zoom around and look at the threshold that I care about just by looking at the raster we just produced. So I'm going to load that raster. Oops, not that one. The raster we just produced using that weighted grid. And this is the one where I'm actually going to change the values so that they're a little more easily visible over the top of my hillshade. And now you can go in and see the accuracy of your culverts and see, is there any places you dramatically missed? Is there any places you care about? Here's one of those instances I was talking about where, you got the stream coming down. We didn't have a culvert. It hits the road and it's just stuck on that side of the road until it finds a place, which is this culvert clear down here. So that might not be representative of that particular stream. So those are the things to pay attention for when you're creating that culvert layer. And this is a good place to iterate. but these might fall outside of our threshold anyways for what the network we're selecting is. Um, so this is a good point at which you can just add back on our flow lines. So there's our network. Um, and this is where, you know, what what do we care about for this particular project? Do we want all these intermittent streams is just perennial? But essentially what you're gonna do is choose a threshold. And this isn't a great example as far as like if you're doing a watershed because we obviously don't have all this upstream drainage area. So um, the values coming in, you know, are starting basically from here. So if we had the full clipped watershed raster, these values would not be the initiation of the channel essentially. So these values would be a lot higher. It'd probably be a lot easier to threshold this. In the case of this project, what was important was basically to this town essentially, or right above town. So we're just gonna say this about here is the where we want our channel to start existing on this main stem, and we want to at least include up to here on this main stem. And so you can use the identify tool and just zoom into those colored pixels on that raster and see what that value is. So it's 18,717. And then up here, I think we're going to be even smaller, 5,000. So you're just going to zoom around. You know, if I was doing it based on the initiation of like the NHD network, you might select these pixels, and obviously you're going to get much lower values, and it's going to be much more inclusive. But for this example, I'm going to use that 5,000. And so I'm going to use this command here, this threshold command. And I'm going to change that threshold to 5,000. And I'm going to run that. And we'll take a look at what that is. So this is going to produce a raster that has your flow lines. And it's helpful to change the symbology. It's either a 0 or a 1, so paladin unique is pretty easy. Make this a color that's easy to see, that I can compare against the NHD, and then turn this off. So you can see how, you know, how much more accurate our channel is now. We have it going through those culverts. But then you'll see stuff like this where, given the threshold we used, we included a stream that we did not have a culvert for. So it's running along the road. And I think I saw that in a few places. Yeah, like right here. So if this was important, you know, here's a place where I would have needed to include a culvert to get that flow path to cut through the road there rather than go down this way. But I'm not too concerned because what I like is my main stem. That's like the tributary of concern. And that seems very accurate for what we want. Another example of where there wasn't a culvert and its flow path is stuck on the side of the road until it can find a way in. So one thing you can do is if we over threshold So I'll do that real quick. I'm just gonna run this again and choose a much smaller threshold. Like 500. And I'll just name this something else. Load that into the map. And now you can see I have a much more extensive network than the other threshold we chose. So you can easily iterate on this. What you can do is if you choose a threshold to include certain things, but it's overextensive, you can convert this raster back to a polygon by using polygonize, and you can actually edit the polygon like so it'd look like this drainage network, and you could go in and manually select segments and delete them, convert it back to a raster to use as the input in the last step, so you can make more of a custom network as far as its extents, but it's still accurate to the flow paths from the flow accumulation. So I'm going to stick with the 5,000 threshold for the example, but the last step is extracting our stream network as well as some other stuff. So copy that, put that in here, and just rename the inputs and outputs. If you don't recognize the input, it is likely an output, or is an output, like all these. I don't have these as inputs anywhere. I didn't create these, so these are all outputs. And then here's one I recognize. This is the input where I could put in that other threshold or the custom one I made. Is that SRC, and we're gonna put in our other inputs. And this gives you some extra stuff too that you wouldn't have if you were using different tools to do this process. Okay, that is done. So I come back here, turn off some of these intermediate layers I had, and I browse to my project folder, and I load that output. It will give you an output shape file called, I named it net. And it's essentially that same, the SRC raster, this one turned into a network. And you also get watershed layer if you want it. But then this is another point. After we get level paths on this, we could go through and delete some of this stuff. Like I'd probably clean those up. But now I have an accurate flow path. If you want to reduce the nodes, you can do a quick simplify on the network. I'm just going to do 1 meter. So it smooths it out a little bit, reduces nodes. Just personal preference if you want to do that or not. And then on this network, I'm not going to cover this part, but there's a few important things that we have that Totem calculates, which is another reason to use it, that are necessary for inputs into the model. So if we look at the NHD attributes, we need these drainage area values. Obviously, we already have slope, and we need F codes. So you might manually have to transfer over perennial versus non-perennial distinctions onto this new network, this custom network. And we need an NHD plus ID, which is basically a unique ID. which the Riverscapes models read those attributes when they're producing VBET. So the next step, like I said, I'm not going to cover it, would be to run this through a custom script that gives it level paths, and then to calculate the math on the contributing area. And there's documentation on what all these fields mean. So upstream contributing area, this is the amount of pixels. So in our case, it's 1 square meter pixels. So you'd have to do the math to calculate that into square kilometers, like it is done in NHD. But basically, we would change the attributes to match the NHD inputs, and then download a Riverscapes project, replace the DEM, and replace the proper networks in the geo package for that, and it will feed all the downstream models.